Sponsored by Incogni. I have a secret. There's something I'm a little afraid of. For the last 9 years, I've been building rockets, and most of them don't fly like your typical model rocket. That's not the secret. I mean, I made a whole YouTube channel out of it, so clearly not what I'm talking about. The thing I'm afraid of is a type of control. It's a technique used to keep a rocket stable. A lot of the rockets I fly don't use fins. They keep themselves on course by using little servos to steer the rocket motor at the bottom. And you can think of this like balancing a stick on your finger. When you tilt the rocket motor to the side, there's a little trigonometry you can use to figure out how powerful that resulting side force will be. That is not what I'm afraid of. In fact, I actually really like trigonometry. Let's just get to the juicy part. The thing I am afraid of is aerodynamic control, using movable fins to steer the rocket. I'm not afraid of it because I haven't tried it. I'm afraid of aerodynamic control because over the last few years, every time I've tried, it hasn't worked. The most serious attempt at aero control was on the project I did with Mark Rober to drop an egg on a guided re-entry vehicle from 100,000 feet. But we couldn't get beyond subscale drop tests. The vehicle would almost instantly lose control. So what makes this hard? Why can't you just tilt the fins in the right direction and steer it where you want to go? The answer to this involves a lot of math, and the good news is we're not doing any of that math today. That is the topic for the next video. Today is all the cool stuff. In this video, I'm going to show you the first time that I have ever gotten supersonic aerodynamic control to work. Before we begin, I want to answer the question of why I want to do aerodynamic control. As you might be aware, I'm on a long journey toward building a space shot, a rocket that goes over 100 kilometers. The burn time on the rocket motors for this will be relatively short, which means that if we use thrust vector control, we'll have large portions of uncontrollable flight. So instead of thrust vector control, we'll use traditional, flat, non-moving fins to keep the rocket on course. This is called passive stability. You point the rocket where you want it to go, you launch with little or no wind, and as long as it gets up to speed quickly, the rocket will fly relatively straight. One of the project goals for the space shot is capturing good footage and images on the way up and while we're in space. And here's the thing about fins on a rocket. You misalign them a little bit, you spin. You have any asymmetries on the rocket body, you spin. You launch on a day that ends in the letter Y, you spin. It's for this reason that I designed a camera spinner to counteract that rotation. The idea was to mount... Oh, man. The idea was to mount all onboard cameras on a large bearing, then spin them at the exact speed and in the opposite direction of the rocket. So while the rocket spins, your footage comes out stable. So if we have this thing on the space shot can spin as much as it wants and we'll still get good footage. There are two things about this approach. Number one, it was stupidly heavy. You hear this? You've got to transfer all of those bending loads on the rocket through a smaller center tube, and the attachment points on either side need to be very well aligned. To be honest, it was kind of a nightmare to build. Two, it's overcomplicated. I mean, when you think about it from a high level, at some point, why don't we just not let the rocket spin? And that is where aerodynamic control comes in. We want to control the roll axis. I want footage that looks like this, but smoother and without the spinning fins. I don't just want to control roll though. The space shot architecture that I've got right now is 2 stages, not 1. 2-stage high-altitude vehicles are notoriously bad for recovery dispersion. That is to say, with no guidance, a 2-stage space shot rocket can easily land 10, 20, 30 miles away, which actually constrains where we can launch this thing pretty hard. Part of that dispersion is wind on the way down, but a lot of it is the second stage pitching over on the way up. No matter how hard you try and point the vehicle upright, there are many contributing factors that will cause it to tip over slightly as it ascends. So what if we just keep nudging it back to upright with some tiny control surfaces? In my mind, we've got two options. Actually, there's a secret third option. Anyway, option one, we add canards on the front of the vehicle. These are little tiny movable fins. With 4 canards, we can move the rocket around in roll, pitch, and yaw. These are seen all over the place on missiles and rockets. Even in amateur rocketry, folks like Jim Jarvis have perfected systems like this. One thing you'll notice with Jim's flights is that the fins at the bottom of the rocket, are spinning. Why is that? The effect of tail fin parameters on the induced roll of a canard-controlled missile. No offense, not a very catchy title, maybe like toss a Mr. Beast face and call it 10 sexy tips to keep it going steady, parentheses, how to prevent your missile from rolling. Anyway, check this out. Canards are attractive devices. I'm telling you, change the title. This is already clickbait. The use of canards as control devices complicates the rolling moment characteristics. As canards are deflected in pitch, roll, and/or yaw, vortices emanating from the canards stream aft and interact with the tail section, which typically induces an adverse rolling moment. The adverse rolling moment can result in a roll reversal if the induced roll from the tail fins exceeds the direct canard roll control, i.e., the downstream effects from the canards can be more powerful than the canards themselves. Oftentimes, a roll mechanism is used in a canard control system to mitigate the adverse roll properties. This has been accomplished with free spinning tail sections, or in the case of the Sidewinder missile, with rollerons. The TLDR is that when you tilt a canard forward of the set of static fins, the vortices that shed off that canard fall back toward the aft fins and can sometimes, not always, generate enough of a low pressure zone to induce the exact opposite control input. It is an inherently chaotic and turbulent phenomenon, and for that reason, it is extremely hard to simulate. Rollerons, by the way, very cool solution to this problem. In the 1950s, when the Sidewinder missile was being developed, the rollerons were added on the missile in part because we had no way to model the complex vortex shedding that comes off of the canard tips. And now, we do have that capability. Now, defense contractors do have that capability, which is why newer versions of the Sidewinder do not feature rollerons, and basically all modern missiles don't have them either. I do think it would be a fun project to fly some rollerons in the future, but I'm not interested in using them for the space shot. I'd like to actively control yaw, pitch, and roll, and we should search for a solution that does all 3 axes at once. With vortex shedding making canards, as the paper might put it, the less attractive option, another solution would be to rotate the aft fins themselves. This is another common approach with modern missiles and sounding rockets. Typically, engineers will design the fins such that they attach right near the throat of the rocket motor's nozzle. If you're careful about thermal management from the rocket motor, and are efficient in your nozzle design, you can jam actuators inside of this free volume and steer the rocket in yaw, pitch, and roll with one set of fins. This, of course, like anything, has pros and cons. Pro, you have lots of control authority. Once you're up at Mach 2, tilting the fin even 1/10 of a degree will generate enormous side forces. If you wanted to make a 90-degree turn, you could do so in a hurry, and that's why this approach is seen on a lot of missiles that need to swoop around pulling high G turns. As for the cons, let me put it this way. I know I joke about being built different, but even in these jokes, I don't think I'm built different enough at both solid motor and actuator design to get this approach to work. And the thing is, it's overpowered for what we need anyway. I'm looking to take a rocket that is 2 degrees off of vertical and make it 0. We need tiny, gentle corrections, not some hard-turning anti-aircraft machine. I just want to go up. Let's recap. I want a set of control surfaces to very gently nudge the rocket back to upright if it tilts over on ascent. We're actively looking for low control authority solution, and this rules out the rotating aft fins. Canards are the next obvious choice, but they suffer from the control reversal phenomena that I do not have the analytical tools to design around. And while the spin can fix the roll axis, I have concerns about how well it will work in pitch and yaw control. To be honest here, there's always going to be like 20 plus ways to solve a problem like this. Genuinely, I mean this, if you were approaching this problem, I'm curious how you would solve it. Do you think it's easier to make the fin can spin? Would you design your own precision actuator to rotate the aft fins? Would you ditch the two-stage approach entirely and go for one enormous single-stage rocket to make the dispersion problem easier? All of these videos are just me trying bit by bit to figure out how to build this space shot. And while the spin can with canards seems like a viable solution, I have another interesting idea that I would like to try. What if we had all the benefits of canards with none of the vortex shedding issues? The way this works, embed the canard in the fin. If we keep the static fins the same size, we can cut out a portion or top or trailing edges, embed a servo inside the fin, and use that to gently nudge the rocket where we want it to go. This approach also means we can tailor the size of the tab to meet the exact control authority we need, while sizing the overall fins to meet the passive stability needs of the rocket. TLDR, we only need small control authority, so we only need small control surfaces. All of this is just theory though, and as we all know, theory will only take you so far. Let's build it. Using Onshape, let's take a look at the plan here. We'll start with a 3D printed fin can around a 2-inch diameter fiberglass airframe. The fin can will be printed as one part, and in order to house the servo, the fins will need to be a 1/2 inch thick. The servo we're using here is a Bluebird BMS A10H, which is the same little guy I've used for my thrust vector controlled rockets. I also designed a mount to hold the Ava flight computer, and then I got to work building. Starting with the small prototype, we're only going to try and control the roll axis. Rockets roll all the time, and if something goes wrong and this doesn't work, the worst thing that happens is it spins a bunch. To secure the servo in place, I potted it in epoxy. The rocket is going to go a little bit above Mach 1, and I want as much strength as I can get in the fins, especially in the hollow section with the servo. We'll connect the servo to a very tiny control tab on a single fin. Not 2 fins, not 4 fins, just 1. This is because the energy it takes to rotate the roll axis is literally hundreds of times less than the energy it takes to rotate the pitch or yaw axis of the rocket. If you calculate the MOI, or moment of inertia, for the 3 axes of a rocket, you'll find that because of how different these values are, we can use asymmetric control on the roll axis and have functionally 0 effects on pitch or yaw. I took 2 run cams and mounted them on board so we'd get some nice onboard footage, one camera pointing down and one pointing out, and as always, they're mounted with about 30 pounds of hot glue. The flight computer is Ava, and it controls the fin tab through a servo cable that runs down the rocket. Actually, to be honest, it was multiple cables. I had a bunch of extra PWM extension cables from other projects, and since this is kinda low stakes, it should be fine to just combine a bunch of cables together instead of splicing into one longer cable. All right, we're 13 minutes into the video, and I promised you supersonic aero control, so it's time for me to make good on that promise. I wrote a bunch of code to control how the little tab moves, and then brought the rocket out to the Friends of Amateur Rocketry test site to give it a try. For this flight, I also prepared a set of flyaway rail guides, which clamp around the rocket on the pad, then release when it launches, which ultimately reduces drag in flight. On this set of rail guides, I glued 2 run cams looking up to watch the rocket as it lifts off.
4, 3, 2, 1, 0. 2, 1, 0.
The first flight looked awesome. Until I looked at the footage. There is no roll control here, and this was a huge disappointment. We're going to talk more about this in the next video, but I ran hundreds of hours of computational fluid dynamics simulations to evaluate how this flight would perform. The folks on the Patreon can back me up, like, All of my updates this winter were about CFD. I had a period of 2 full months where the only thing I did was spend my time dialing in these simulations to get this right. And to remind you of the stakes, if I can't figure this out at the small scale, I certainly can't figure it out for the space shot. Even the shots that I got from the flyaway rail guides weren't good. One camera failed to record completely, and the other one was kind of out of focus. I guess it's not that terrible since it's, recording in slow motion, but wait, hold on, let's just go back. What is that? What is that?
It should be fine to just combine a bunch of cables together instead of splicing into one longer cable.
I don't know if you've already put the pieces here together, but your boy, Joseph Bislington, in his infinite wisdom, clamped the flyaway rail guides just forward of an exposed servo connector such that when it launched, the guides disconnected the servo. So I have no valid roll control data from the test. I guess that's it for this video. Thank you guys so much for watching.
You can't end it like that.
What?
You promised supersonic aero control.
On Flight 2, I rebuilt the fin can since it's easy enough to print and I wanted another shot at this rocket from the ground up. I spliced the servo cables so that all connections were soldered without the possibility of detachment and used longer cables to keep those to a minimum. I also switched from flyaway railguides to 3D printed railguides. I potted the long servo cable in CA glue, which did a good job of sealing and protecting it against getting damaged or ripping off. CA, as opposed to epoxy, also left the surface of the fin much cleaner this time, especially after painting over it. I also switched over to fancier onboard cameras for this flight. I'm doing a future video on onboard cameras, but the new cameras are GoPro Hero 10s that I tear apart and deconstruct. They shoot at 4K, 120 frames per second, they are beautiful, very difficult to work with, and they barely fit inside of a 2-inch airframe. They're mounted on here using a copious amount of epoxy loaded with Kevlar pulp. I see this, I see the way it looks. I am not proud of everything I do. Thankfully, we don't have time to talk about how gross this looks because it's time to head back to FAR to launch this thing again.
1, 0.
Great up. Another gorgeous ascent here visually speaking, but I also knew right away that the roll control had done something right by looking at the telemetry.
Okay, 2 kilometers. 2.2, 2.3, 2.4.
Although it's low update rate, we can compare the roll set point to the roll attitude in degrees. The numbers are very close for a good portion of the flight up.
Oh my god, I think it worked. Dude, it definitely worked.
It actually worked way better than I thought it would. Let's get the hard part out of the way first. There is no onboard footage. The GoPros did not start recording for whatever reason. Actually, that's not totally true. Maybe that's not the way to phrase it. We do kind of have onboard footage. I'll explain in a minute, but first let's look at some flight data. Plotting the data from the flight here, let's start with vehicle acceleration on ascent in meters per second squared. We'll toss velocity in there as well. You can see the burn from the rocket motor, the immediate deceleration from drag, and the slow tail off as it gets to the peak of flight. Next, we'll plot the roll set point. This is the desired roll angle in degrees on the rocket. Our goal is to roll slowly to 90 degrees and then back as a little roll program to see how well the system works. Now we'll plot the roll angle in degrees from Flight 1. This is the exact same rocket, but with no roll control because of that disconnected servo cable. The rocket is spinning constantly, so our roll angle rotates quickly between negative and positive 180 degrees. Finally, let's remove the Flight 1 data and plot Flight 2. At first we see some disturbances in the roll control, but soon after the system locks in and follows that set point closely. In fact, near the end of the ascent we're so close to 0 degrees that it's difficult to pick out the roll angle from the set point. As we near apogee, roll begins deviating again while we lose speed and thus lose control authority. Let's focus in on the initial oscillation at launch. Our maximum velocity was 433 meters per second, and this was reached 500 meters AGL, or above ground, but 1100 meters above sea level, putting our max speed at Mach 1.3. On the plot, I'm also going to mark Mach 1.2 and Mach 0.8. The area between these two is the transonic region. This area of flight is particularly hard to manage, and if you'd like a video about why that is, definitely let me know. I would like to do one. For now, what I want to point out is that our greatest disturbances happen in this region, both while we're speeding up and while we're slowing down. In fact, the disturbance almost seems to start correcting itself once we pass through Mach 1.2 and most flow around the rocket is supersonic. I'm reading the tea leaves pretty hard here. Or put another way, I'm drawing a lot of conclusions from what amounts to about 3 seconds of flight data. We're going to get more flight data in the next video, so make sure you're subscribed for that, but for now, we do kind of have some onboard footage. I sent flight data out to a few folks who volunteered their time to use that data to create animations of the flight. Since Ava tracks 3-axis orientation, velocity, GPS, altitude, etc., that data could be used along with a CAD model and terrain maps to see what the GoPros should have seen. I want to give a huge thanks to Dan, Andrew, Matt, and Gabriel for working on this and allowing the flight to be seen so much more clearly. With a perspective like this, it's much easier to visualize how stable the flight was in the roll axis. Even the disturbances after launch don't roll us past 1/8 of a rotation. Matt here modeled the far satellite imagery, and it's sweet to see the perspective change as we get higher in the air. You can also see the phenomenon we talked about earlier, which is that as we get closer to the peak of flight, we arc further and further over with no pitch or yaw control. Gabriel got a really fantastic perspective here with the body axes labeled and terrain in the background. This was done using ANSYS AGI Systems Toolkit, which is specifically built for aerospace mission engineering and analysis. He also modeled the field of view that both cameras would have had on the way up had they actually been recording. Finally, my buddy Dan worked in Unity to create a whole suite of options for visualizing the data from multiple angles with the real data streaming in the top right. We can also get a sweet perspective of the trim tab doing its thing during flight. One thing to note is how little the tab actually moves. This is again because of how sensitive that roll axis is. It takes almost no force to push it around. On the roll program transitions, we get some really wild oscillations, which were caused by a programming bug on my end, but things were clearly still smooth enough for a solid flight. This is huge. This is much smoother flight data than I anticipated, and it gives me confidence that we can keep moving forward toward a full 3-axis controlled space shot and solve some of these dispersion issues. I will still need a lot more subscale flights that focus on pitch and yaw, and those of you with a keen eye may have noticed there's a ton of detail missing in this video. Hundreds of hours of CFD, massive spreadsheet lookup tables, fin tab sizing analysis. All that stuff isn't here because it's in the next video where I'll cover why this stuff is so much harder than thrust vector control. If you want to see that stuff right now, there are 3 unlisted videos where you can watch me figure out these things in real time over on the BPS Patreon, which is linked below. Every 2 weeks, I toss a new video out there where you get a behind-the-scenes look at a more polished video like this before it comes out on the main channel. Thanks so much to the folks who support over there, and as the rockets get larger, the cost of them does not seem to be going down, so I really appreciate the support. Finally, I would like to thank the sponsor for today's video, Incogni. Each day you spend online, almost no matter what you do, data is collected about you. Some of it is data you're aware of. Maybe you sign up for something with your name and your email. Maybe you put your age in for some birthday calculator. I don't know what you do online, dog. The thing is, there's also some data collected about you that is tied to you and you aren't aware of it. Your browser history, your shopping habits, maybe you're someone who buys a lot of rocket propellant chemicals. That kind of stuff gets bundled with your name and sold to the highest bidder. These companies are called data brokers. Doesn't it feel like you should be in control of where that info goes? The good news is you can be, and the bad news is that there are so many companies collecting this stuff that getting each one of them to delete your data would take ages. So the other good news is that Incogni can take over that task for you. Incogni is a service that reaches out to these data brokers on your behalf to request removal of your data and deal with the process if the companies aren't super cooperative. They monitor for data breaches and overreaches and monitor things while you're on the beaches. That is to say, they work 24/7 24/7 on the clock to make sure your data isn't out there on a bunch of marketing lists or worse. I place a lot of value on this personally, as it's a nightmare to try and hunt this stuff down yourself. So if you want to give Incogni a shot, you can use the link in the description below to get 60% off an annual Incogni plan. That is 60% off a whole year of keeping your data safe. Thank you so much to Incogni for sponsoring this video, and thanks to you for watching. My name is Joe Barnard. May your skies be blue and your winds be low.